Let's talk about flying robots. This is the topic that is part of Chapter 3, Mobile Robots. Flying robots or unmanned aerial vehicles, UAV, are becoming increasingly common and span a huge range of size and shape as shown in figures 13 to 16. Applications include military operations, surveillance, meteorological observation, robotics research, commercial photography, and increasingly hobbyist and personal use. This is the Global Hawk Unmanned Aerial Vehicle UAV, and it is a fixed wing UAV. It's called fixed wing because the wing is fixed in its position. It does not move. This is a micro air vehicle, MAV, because it's small. And this is a 1 gram coaxial helicopter with 70 mm rotor diameter. So this is a type of rotorcraft UAV, and specifically it's called coaxial helicopter because it has two counter-rotating coaxial rotors that rotates in the opposite direction. So you can imagine if this rotates in clockwise direction, this rotor will rotate in the anti-clockwise direction. And this is a quadrotor which has 4 rotors and a block of sensing and control electronics in the middle. So this is a quadrotor because it has 1, 2, 3, 4 propellers. And this too is a rotorcraft UAV. And one of the clear advantages of rotorcraft UAV is that it can vertically take off and land. Additionally, it can hover at a constant position. So if we compare this with a fixed wing UAV, this type of UAV is not able to vertically take off or land or hover, and it is a runway such that it needs to move up to a certain speed. Only then will be able to fly or lift. But a rotorcraft UAV, it does not need a runway, as you know, and it can take off vertically and land vertically as well. So flying robots, they differ from ground robots in some important ways. First of all, they have 6 degrees of freedom, which means a flying robot such as a quadrotor can move in the X, Y, Z direction, and it also rotate in X, Y, and Z axis. Secondly, they are actuated by forces. That is, their motion model is expressed in terms of forces, torques, and accelerations. If we look at our quadrotor, for example, there is a mechanism to apply torques on each of these propellers, and these torques will rotate our propeller such that it will push down air through it downwards. And because there will be a flow of air masses downwards, there is an opposing force upwards that we will call thrust, and that will enable the rotorcraft to fly. So in this section, we will create a model, which means a mathematical equation governing the behavior or the dynamics of our quadrotor, as shown in figure 16. Quadrotors are now widely available both as commercial products and as open source projects. Compared to fixed wing aircraft, they are highly maneuverable and can be flown safely indoors, which makes them well suited for laboratory or hobbyist use. Compared to conventional helicopters with large main rotor and tail rotor, the quadrotor is easier to fly, does not have the complex swash plate mechanism, and is easier to model and control. So the notation for the quadrotor model is shown in figure 17. This is a figure that represents our quadrotor. As we can see, there is a coordinate frame that we call B. This is the body attached coordinate frame that has its x-axis downward following the aerospace convention. It has 4 rotors: rotor 1, rotor 2, rotor 3, rotor 4, mounted at the end of each cross arm. Hex and octo rotors are also popular, with the extra rotors providing greater payload lift capability. The approach that we will describe here can be generalized to N rotors, where N is even. And these rotors are driven by electric motors powered by electronic speed controllers. And some low-cost quadrotors use small motors and reduction gearing to achieve sufficient torque. So if we analyze this figure, first of all, we can see there are 4 rotors or propellers. This is, you can call this a rotor 1, rotor 2, 3, 4. And this indicates the angular velocity, right? Omega, let's call this omega. So this is omega 1. As you can see, omega 1 and omega 3 is counterclockwise, right? Rotors 1 and 3 rotate counterclockwise, but rotors 2 and 4, they rotate clockwise. And there's a reason why this is the case, as we will explore later. And this is the body attached coordinate frame. X is the heading. That means so this points to the front of the quadrotor. This is Y and this is Z. So this is body attached, which means this coordinate frame you can imagine as to be affixed to the quadrotor. And this symbol here represents the center of mass, and T is the thrust. So T1 is the upward force or thrust generated by rotor 1. We have T1, T2, T3, T4. The rotor speed is omega I, as I've said earlier, and the thrust is an upward vector. And the equation that governs the thrust, or the equation that gives us the relationship between the thrust and the omega, is given by equation 1, where Ti is B multiply omega I squared. So because we have T1, T2, T3, T4, T1 is B multiply omega 1 squared. And T, as you can see, T1, it points in the negative Z direction because it's upwards. Here B is always positive. It's a lift constant that depends on the air density, the cube of the rotor blade radius, the number of blades, and the chord length of the blade. So for example, if you have a quad rotor with a specific dimension or specification of the propeller, so B will be different. So it really depends on the type of propeller that we use. The translational dynamics of the vehicle in world coordinates is given by Newton's second law. This is given by this equation. So as you can see, this is the translational dynamics. Alright, so V is velocity of the vehicle center of mass in the world frame. G is the gravitational acceleration. M is the total mass of the vehicle. B is aerodynamic friction. And T is the summation of all the Ti, which means T is T1 plus T2 plus T3 plus T4. It is the total upward thrust. So in order to have your velocity, you have to integrate this, right? So V dot, when you integrate, you get V, right? When you integrate V, you get the position. So as I've explained, the first term is the force of gravity, which acts downward in the world frame. The second term is the total thrust in the vehicle frame rotated into the world coordinate frame. And the third term is aerodynamic drag. And that's why it has to be minus. It has to be subtracted from the whole equation because it's opposing the motion. So pairwise differences in rotor thrusts cause the vehicle to rotate. Okay, so now we will explain why these rotations are different, right? So the torque about the axis of the vehicle, or the rolling torque, is generated by the moments this tau x. So tau x is the torque, which is equivalent to d multiply t4 minus d multiply t2. So d is this, the length of this arm, and if we want to rotate the quadrotor in the positive x direction, so you should know by now what is positive rotation and what is minus rotation. So if you are looking, if you have your eyes here and you're looking towards in the direction of the x-axis, clockwise rotation is positive and anti-clockwise rotation is negative. So if I want to rotate the quadrotor in the positive direction of, or should I say, rotate around the x-axis, positive rotation around the x-axis, I need to generate more T4 compared to T2, right? If T4 is higher than T2, then the quadrotor will rotate in a positive direction about the x-axis, right? Which is given by this. So positive torque means T4 is greater than T2, okay? And because Ti is given by b omega I squared, we can rewrite this as equation 3. So now tau x, or the torque around x-axis, is dB multiply omega 4 squared minus omega 2 squared. And similarly for y-axis, the pitching torque is given by this. Okay, let's look at pitching torque. So pitch, so roll is rotation about x-axis, and pitch is rotation about y-axis. Okay, so positive pitch means we rotate in the positive direction about y-axis. So if I want a positive rotation, I need to give a positive torque, which means T1 has to be greater than T3, right? As you can see, if T1 is greater than T3, the quadrotor will rotate this way, okay? And that's why tau y is dt1 minus dt3. Okay, the torque applied to each propeller by the motor is opposed by aerodynamic drag. So what is this? Q. First of all, Qi is given by k omega I squared. If you see, it's quite similar to our thrust equation, but instead of B, now we have K. And K depends on the same factors as B. So this torque exerts a reaction torque on the airframe, which acts to rotate the airframe about the propeller shaft in the opposite direction to its rotation. So it's like when you are driving in your car and you stick your hand outside, you can sense that the air will be pushing your hand backwards, and you have to exert a force to keep your hand in place. So similarly here, when the propeller rotates, it will go through the air resistance, and the air mass will be pushing the propeller in the negative direction, opposing it, and this is aerodynamic drag. So the total reaction torque about the x-axis is given by this, where the signs are due to different rotation directions of the rotors. So you have three torques that we have seen so far. We have the rolling torque, which is the rotation about x-axis. We have pitching torque, rotation about y-axis. And this is the reaction torque, which is the rotation about the z-axis. Therefore, a yaw torque can be simply created by appropriate coordinated control of for rotor speed. So if you want to rotate the quadrotor either clockwise in the positive direction or in the negative direction about z-axis, you just have to control the speed accordingly, according to this equation. For example, if omega 1 squared plus omega 3 squared is greater than omega 2 squared plus omega 4 squared, then your quadrotor will rotate in the positive direction of the z-axis, or positive direction about the z-axis. However, if omega 2 squared plus omega 4 squared is greater than omega 1 squared plus omega 3 squared, then your quadrotor will rotate in the negative direction about the z-axis. So the total torque applied to the mainframe, to the airframe, according to equations 3 to 5 is tau x, tau y, tau z. Once again, this is the rolling torque, pitching torque, and the reaction torque. And the rotational acceleration is given by Euler's equation of motion, given by equation 6, where J is 3 by 3 inertia matrix of the vehicle and omega is the angular velocity vector. So previously you saw the translational dynamics given by the Newton's equation, but this is the rotational dynamics given by Euler's equation of motion. Remember, I told you a rotorcraft, in particular, we talk about the quadrotor. It has 6 degrees of freedom, right? It can move in a translational motion in x, y, and z direction, and it can also rotate in about x-axis, it can rotate about y-axis, and it can also rotate about z-axis. So therefore you need 2 sets of equations as given by equation 6 and equation 2 to describe the dynamics. So the motion of the quadrotor now is obtained by integrating the forward dynamics equations 2 and 6, where the forces and moments on the airframe are functions of the rotor speeds. So by integrating equation 2, you would get the velocity and the position, and by integrating equation 6, you will get the angular velocity and the angle. So next, if you try to put the equations presented earlier in a matrix form, you will get this. As an exercise, can you please try to figure out how to derive this equation? So this equation says thrust, which is T1 plus T2 plus T3 plus T4, and tau is given by tau x, tau y, tau z, is equivalent to this matrix, which we will call matrix A multiply omega 1 squared, omega 2 squared, omega 3 squared, and omega 4 squared. So this equation means if you set your rotation of the propellers or the rotors accordingly, you would have certain values of the thrust and the torque. So this matrix is constant because it depends on B, D, and K, and it can be inverted if these constants are positive, right? Which indeed these constants are positive. So in order now, if we have required thrust and required torque, we can compute what is the needed angular speed of our rotors in order to generate the required torque and thrust by inverting matrix A. So if T tau is given by A multiplied this, so the angular speed is given by A inverse multiply T and tau. And this is used to solve for rotor speeds required to apply a specified thrust T and moment tau to the airframe. So now, if I know I need a specific value of thrust, a specific value of tau x, tau y, and tau z, I can compute what is the angular speed that we need to generate in our quadrotor. Because you know that if we look at our quadrotor, the main control input is simply the angular speed, right? So this, the way our propeller rotates, or the angular speed, how fast it is, that will produce required torque and thrust. But of course, how do we generate that angular speed? You need to provide torque, right? So yeah, so as we will see later, in order to move our quadrotor to a certain position in the world coordinate frame, the last stage of our control action is to generate the required angular speed. And we can do this if we know what is the thrust and the torques that we need. And this equation will be used for that purpose, as we will see shortly. Now let's study how we can control our quadrotor, or any quadrotor for that matter. So this is a Simulink model, and the name of the model is SL_quadrotor, which is a closed loop simulation of the quadrotor. And as you know, Simulink is part of Matlab. But in order to have this model, you need to have the toolbox installed. And the name of the toolbox is Robotics Toolbox for Matlab. So I'm sure you don't have it yet. So if you go to Google and type Peter Cork, and the first result is a website of this roboticist. You go here, go to toolboxes. There are many toolboxes that he created. Go to the first one, and there is an instruction here on how to download and install the toolbox in your Matlab. Okay, the version of Matlab that I use is Matlab 2019A, which works fine with this toolbox and simulation. All right, and this is licensed by UTM. You have to download and install, and if I'm not mistaken, I'm not sure if you can use it from home during this movement control order, but we will talk about that some other time. But for now, so once you have downloaded and installed the toolbox, you can check if it is here in your Matlab by typing VER. So it will list all of the toolboxes that you have, and look for Robotics Toolbox for Matlab. So this is the toolbox that you have just installed that we'll be using. Okay, so now if you type SL_quadrotor, it will load and open the model. So this is how it looks like. Okay, you can go ahead and run it. Another window will pop up showing the quadrotor flying. So if everything is okay, you can see this simulation. So this simulation, first of all, involves the mathematical model governing the quadrotor, equation 2 and 6. As you know, equation 2 is the translational dynamics, equation 6 is the rotational dynamics. And we have to design a controller now in order to generate appropriate values of rotor speeds such that it will move as we desire. So I will close this now, and let's get back to our block. So if you have this, you can analyze it one by one to make sure what is happening there. And for better clarity, I have drawn this here. So as we can see here, there are a number of controllers involved. So this is the velocity controller. Here we have attitude controller. So attitude here refers to the angle of the quadrotor. We have roll angle, pitch angle, and yaw angle. This is the yaw control, which means this attitude controller specifically controls the roll and pitch angle. So roll here refers to the angle about the x-axis, pitch here is angle about y-axis, and yaw is the angle about z-axis. We also have height control, okay? And all these outputs of these controllers or control outputs will go to the control mixer. So this block implements the equation that we saw earlier. This equation, okay? So the input to this block is required tau x, required tau y, required tau z, and the output is omega 1, omega 2, omega 3, omega 4. And this is your system, the quadrotor. So in this block, there are mainly two equations, equation 2, which is the translational dynamics, and equation 6, which is the rotational dynamics. And the output of this block, which is your quadrotor, the output here is roll angle, pitch angle, yaw angle. We have the velocities, and we have the rate, the velocity here. Let me repeat. We have the x position, y position, z position, x velocity, y velocity, z velocity. We have roll angle, pitch angle, and yaw angle, and the derivatives, which means the roll rate, the pitch rate, and the yaw rate, or the angular velocity. All right, so 12 outputs here, all right, representing the state of the quadrotor. And we have desired position here, x and y. We have desired yaw angle, and we have the desired z position. Okay, so desired x, y, z position, where we want the quadrotor to go, or in which trajectory it should follow, and we have the desired yaw angle. Okay, note that here we don't have desired roll angle, we don't have desired pitch angle, because for this particular application is not required. Now let's go back to the slides. So next we will design some controllers. So in particular we have position controller. Here this is a velocity controller. This is attitude controller. We have a statement on yaw controller, and finally one more equation on altitude controller. So note the difference, okay? Attitude, we talk about the angle, roll angle, pitch angle, and yaw angle. But altitude, we talk about the height, the z position of the quadrotor with respect to the world coordinate frame. So let's start with the first one. This is the position controller. So if we look at our model, the position controller sits here. Okay, and the input to our position controller is the actual, this is the actual x and y position. This is the desired x and y position. So in these equations, every variable with a superscript asterisk or star refers to desired, and superscript hash symbol refers to actual or the measurement. So here, this is the position controller. So this is the desired position. This is the actual position. Okay, and ROB prime is the rotation matrix from chapter 2. All right, and what does this represent? So this will map our velocity from world coordinate frame to B prime coordinate frame, and it's explained here what is B prime. So B prime is again attached or affixed to the vehicle. It has the same origin as B, but with its x and y axis in the horizontal plane and parallel to the ground. So you have to imagine there's another coordinate frame, B prime, which has the same origin as B, but is parallel to the world coordinate frame or parallel to the ground. So it should look something like this. Okay, so if this is your quadrotor top view, we have the B coordinate frame, right, which I explained earlier. It is affixed to the quadrotor, and from side you can see X and Z. So this is thrust 1, thrust 3, and the total thrust is summation of everything. And there's another coordinate frame that we have just defined. We call it B prime. So if the quadrotor is tilted while XB is pointing this way, XB prime is always parallel to the ground, but the origin is the same. And ZB is always this way, in the direction of gravity. Okay, XB prime, ZB prime, but ZB is parallel to XB. So that is our new coordinate frame. So this equation, what it does is that it maps, or it changes the vector v star 0 to v star b prime. Okay, so let's look at, so where is this? So this is, if we look at our, so this is here, right? If you can see, the output of position controller is v star b prime. The output of position controller is v star b prime. So what is this? V star b prime is desired velocity with respect to b prime. Kp is the proportional control gain. However, if you look at the model, like I said earlier, this is our position controller, but you cannot see Kp here. So that shows the Kp that they have implemented is probably 1. Okay. So next, let's look at the velocity controller. So one thing you have to notice is the output of our position controller, which is v star b prime, becomes the input to the velocity controller. Okay, and the output of the velocity controller is desired pitch angle. So this velocity controller, the output is the desired roll and pitch angle. So even though in the slide only one equation is shown, but in the Simulink model there's another another equation similar to this that computes theta r star. So this is theta p star. This is a desired pitch angle, and there is another equation which outputs desired roll angle, and these terms will be vy star with respect to B prime and Vy hatch with respect to B prime. Okay, so here this term is the actual velocity, Kf is the controller gain. So the output is the desired pitch angle, and this becomes the input to the next controller, that is the attitude controller. So this is the attitude controller. So the output of the previous controller goes to attitude controller. And the output of the attitude controller is tau x and tau y desired. So here is this is the equation for tau y star, which is the desired pitching torque. But in the model, there will be another equation for desired rolling torque, tau x star, which uses theta r star and so on. And in this equation, first of all, k tau p and k tau d are the proportional and derivative controller gains. These are actual pitch angle. This is actual rate of pitch angle, or the angular speed. So we have a control block called the Yaw Controller. This will determine error in heading angle and implements a proportional derivative controller to compute the required yaw torque, which is achieved by speeding up one pair of rotors and slowing the other pair. So let's look at yaw control. So in our Simulink block, this is where the yaw controller is, and the input here is the desired yaw angle, and the output is tau, the desired tau z. Okay. Height controller, or the altitude controller, is given by this. The output of the altitude controller is thrust, right? And the input is the desired x position, or the height, desired height. So in this controller, we have Kp, Kd, which is the proportional and derivative controller gains. We have another term called T0, and T0 is mg, is the weight of the vehicle. And this is an example of feed-forward control, used here to counter the effect of gravity, which otherwise is a constant disturbance to the altitude control loop. And then finally, we have the control mixer. Like I said, it takes in desired torque and desired thrust and generate the required angular velocity, or the rotor speed of the quadrotor. So these are the input to the quadrotor block, which implements the forward dynamics integrating equations 2 and 6 to give the position, velocity, orientation, and orientation rate. So here position is x, y, z, and velocity is vx, vy, vz. Orientation here refers to theta, theta x, theta y, theta z. Orientation rate refers to theta x dot, or theta dot y, theta dot z. So basically this is how it looks. So if you could redraw this in the usual control block architecture that you are familiar with, this is how it looks like. Okay, so we have a quadrotor. Once again, this in this Simulink model, this implements equation 2 and 6, the translational and the rotational dynamics. The output of this block is the XYZ position, XYZ velocity, the roll pitch yaw angle, and the rate of the angles. Okay. So in order to make the quadrotor to move to a certain position, which is given by our reference X and Y position, we compare it with an actual X and Y position, we feed it to our position controller. The position controller will generate desired velocity with respect to the B prime coordinate frame. This will be compared to the actual velocity with respect to B prime frame. It goes to the velocity controller, which generates our roll and pitch angle, the desired roll and pitch angle. This will be compared to the actual values, fed to our attitude controller, which will then generate the desired rolling and pitching torque. So if you look at the flow, in order to achieve desired position, we have to know we have to compute the desired rolling and pitching torque. For this controller, the Yaw controller, on the other hand, we have desired theta y, which is the yaw angle and the rate. We compare it with an actual yaw angle and the rate. It goes to the yaw controller and we generate the desired yaw torque, or the torque about the z-axis. And finally, for the altitude controller, in order to achieve the desired height, we have to generate or compute the desired thrust. So all these are desired, right? So this is the desired torque values and the desired thrust, and the control mixer will give out the required rotor speed to achieve, that will generate this required or desired torque and thrust, and those values will go to the quadrotor. So in a way it's a bit different than other systems that you have seen, because in order here to minimize the position error, we have to compute one by one quantities, or quantities one by one, until we get to the desired torque value and the thrust value. So from position, we have to compute desired torque and thrust. So why this happens, right? So let's go to the slides back. So to recap, a position error results in a required translational velocity. To achieve this requires appropriate roll and pitch angle so that a component of the vehicle thrust acts in the horizontal plane and generates a force to accelerate the vehicle. So here, so if we look at the simple diagram, so in order to make the quadrotor to move from a position to another position, let's say around here, we have to tilt the quadrotor. We cannot just move it from the initial, let's say initially it was like this. We cannot just move it left and right without tilting it. It has to be tilted. Why? Because if it is tilted, thrust remains pointing in this direction, but now we can break thrust into its x and z component. So this becomes thrust x b prime, and this is tz b prime. And because we have a z component, now the quadrotor can move this way, you see. So the point here is, if you want to move the quadrotor either left or right or anywhere, you have to tilt the quadrotor. And in order to tilt it, you need to know how much to tilt. So hence, that's why we saw earlier, we have cascaded control system, right? Just because we want to minimize the position error, we have to generate desired torque. because without torque, the quadrotor will not be tilted, and therefore it will not move this way, and therefore you cannot minimize your positional error. So as it approaches its goal, the airframe must be rotated in the opposite direction so that a component of thrust decelerates the motion. To achieve the pitch and roll angles requires differential propeller thrust to create a moment that rotationally accelerates the airframe. So this indirection from translational motion to rotational motion is a consequence of the vehicle being under-actuated. We have just 4 rotor speeds to adjust, but the vehicle's configuration space is 6-dimensional. So this phrase here, translational motion to rotational motion, is shown here, right? This is translational motion and this is rotational motion. So in the configuration space, we cannot move in the X or Y direction, but we can move in the pitch or roll direction, which results in motion in the X or Y direction. That means we cannot directly move immediately in the Y or X direction. We have to first move in the pitch or roll direction, and then that will result in the motion in the X and or Y direction. Well, the cost of under-actuation is the maneuver, and here the roll and pitch angles are a means to achieve translational control and cannot be independently set. So that's all for this chapter. Please look at the tutorial questions for further understanding and discussion. Thank you.